We're going to wrap up our discussion of the wave behavior of light by talking about thin film interference. And thin film interference happens all the time when you blow a bubble. When you see the rainbow pattern of colors, that's thin film interference. When you see that rainbow pattern on like an oil slick, that's thin film interference. A thin film is anything, any material that has a thickness, which we're going to call T, smaller than a few times the wavelength of light. So this thickness is going to be on the order of a few nanometers. Okay, so this is a really thin layer of stuff. Okay, and you're going to have constructive and destructive interference to create that sort of pattern of color that you see from thin film interference. So what's happening in thin film interference is that you're going to have light that gets reflected off the top surface of that film, light that gets reflected from the bottom surface of that film, and then both of those reflected lights interfere constructively or destructively in order to produce this pattern that we see. To state that point again, a light wave is partially reflected from any boundary between two transparent mediums with different indices of refraction. Okay, so you're always going to have reflection off the top boundary, and then that light is going to be, some of that light gets refracted into the film, and some of that light will be reflected on the front of that film, but also off the back surface of that film. That essentially gives you two reflections. And again, those reflections can interfere constructively or destructively. So here we have an example. We have a candle here, and we've got a pane of glass. And we see two reflections, one that's coming from the front surface of the pane of glass, and one that's coming from the back surface of that pane of glass. So here we have examples of how this light gets reflected. Now, here's our boundary between two mediums with different indices of refraction. Now, a light wave undergoes what we call a phase change if it reflects from a boundary at which the index of refraction increases. Okay, so a phase change essentially inverts the waveform. It flips the waveform. This is the same as shifting your wave either forward or backward by half its wavelength. So this is what we call a phase change. So here, let's see, we've got two materials with two different indices of refraction. Here we have our incident wave through the first medium, and then it's going to transmit through the second medium, okay? So some of this light is always going to get refracted or transmitted or sent through the second material. Now, if this index of refraction through which the light is moving first is greater than the index of refraction of the second material, then our reflected light wave does not have a phase change. And so the light that comes in has the same pattern as the light that comes out. The same pattern, like we've got the crests of the wave where the crest should be, the troughs where the trough should be. That same waveform that's coming in gets reflected back in the same way. But if we have a case where the index of refraction of the first material that wave moves through is less than the second index of refraction, or the index of refraction of the second material, then our reflected wave does have a phase change. That phase change is different by half the wavelength. And what that essentially means is that in this case, our reflected wave gets inverted compared to the original wave that was coming in. Here we have a figure that I'm going to be using essentially for the remainder of this mini lecture. We've got three layers of material. We've got our light coming in through a material with an index of refraction of N1, and it gets reflected off of that front surface, okay? And then some of that light gets refracted or bent through the second material, sent through the second material, and then that light strikes the boundary between this material and then the third material. And when the light strikes that boundary, it also gets reflected back to our eyes. So what we're seeing here, if this is our thin film right in here with a thickness of little t, we've got the light coming in, reflecting off this top surface, and then bouncing back, okay? And then we have the light coming in, it gets bent through the medium, reflecting off the back surface, and then coming back to our eyes. And so it's the interference of both of these rays that get reflected from the top layer and the bottom layer of our thin film that produces the interference that we see with our eyes. That's the rainbow slick pattern, you know, in an oil spill, or that's the rainbow pattern on the surface of a bubble. Now, how do we determine whether our resulting interference that we see appear with our eyes is constructive or destructive? In order to do that, you have to think about the indices of refraction and whether or not there's a phase change when there's a reflection of the light from the different material. Okay, so for example, here we have our substrate again, our thin film. If the index of refraction of the thin film is greater than the medium through which the light was traveling through first, then right here at this boundary, there's a pi/2 phase shift in the reflection at the boundary. So we inverted our waveform for the reflected light. Okay, and then when that light comes through here, if the index of refraction of this third layer, the layer outside the thin film on the other side, is greater than the index of refraction of the thin film, then there's also another pi/2 phase shift in the reflection of the light at this bottom boundary. Okay, and then that light gets reflected, we invert the waveform, and then that comes back to our eyes. And so it's the combination of these reflected waves that determine whether or not we have constructive or destructive interference. But then because of the indices of refraction, for this particular example, where we've got N1 is less than N2 is less than N3, then we have a pi/2 shift in the wave at both of these boundaries when the light gets reflected. These reflected waves, when we see them with our eyeballs up here, will appear to interfere constructively, that means add up to produce the bright points, if their path difference is an integer number of wavelengths, kind of like when we were thinking about the single slit and double slit diffraction. So, you know, our wave that bounces off the first boundary, you know, it comes in, bounces back. But the wave of light that strikes the first boundary transmits through the thin film and then gets reflected off the bottom and then goes back out again. This second wave has to travel an additional distance of t, so the thickness of the film, down, strike the back of the film, and then pop back up another distance of t. So it has an extra path length, possibly, of t plus t, so 2t. So if the path difference between this wave that reflects off the top of the film and the wave that reflects off the backside of the film, if that path difference is an integer number of wavelengths, then we have constructive interference. So in this case, we would have 2t is equal to m, that's our integer number of wavelengths. Are we thinking about the first order reflection, second order reflection, third order reflection, and so on, times the wavelength. And this is the wavelength of light inside this material. And we already saw that you can find the wavelength of light inside a material, and that's equal to the wavelength of light in a vacuum outside the material divided by the index of refraction, okay? And then these reflected waves will interfere destructively, so give us dark fringes, if the path difference is a half integer number of wavelengths. So m minus 1/2 times lambda n has to equal 2t. Remember, t is the thickness of our film, m is our integer number of wavelengths, okay? And so for thin films, we start counting at m is equal to 1. So your first order constructive or destructive interference, m is equal to 1. Your second order, m is equal to 2. Your third order, m equals 3, and so on. So how are we going to figure out which equation we're going to use for constructive or destructive interference for a thin film? It all has to do with our order of the indices of refraction and which materials have larger or smaller indices of refraction. We're going to use this handy, what I'm going to call, thin film truth table to help us figure out whether or not we have constructive or destructive interference with our thin films. Okay, so how do we work this? Well, in the problems, I will always tell you what the index of refraction is for any of our 3 layers. And then you have to figure out, okay, think about which layers of the material have larger or smaller indices of refraction. And that will help us figure out the constructive or destructive interference. So in this table, it's also on your equation sheet, so you get this for your exam, okay? The first column asks us, is N2 greater than N1? Is that true or false? Okay, so depending on the problem, I'll tell you what the indices of refraction is for N1, for the first material that the light encounters, and then the second material that the light encounters. And N2 is always the index of refraction of your thin film. So if N2 is greater than N1, index of refraction of your thin film is greater than the material that the light moves through first. That's your incident material. If the light is incident inside a material, that's the material that your wavelength of light goes through first. Okay, so our wavelength of light is coming through a material with index of refraction of N1 here. So that's our incident index of refraction. So if the index of refraction of our thin film is greater than N1, then we would say true for this condition. Is N2 greater than N1? True. That's true for both of these bottom ones here. Is N2 greater than N1? If it's false, we're up here. And then we have to think about what is the index of refraction of your third material underneath your thin film. If the index of refraction of the material underneath your thin film is greater than the index of refraction of the thin film, then you would say, is N3 greater than N2? If the answer is true, yes, based on your problem, then you're going to look for these columns where we have, or these rows where we have true. If N3 is greater than N2, you would say true here. If N3 is less than N2, you would say false here. So if you have a problem where N2 is greater than N1 is true, and N3 is greater than N2 is true, you look for the row where both of those conditions are true. And then you come over here and it tells us exactly the equation we're going to use for constructive or destructive interference. This is way better than what I had to do when I was taking physics and I had to memorize like the orders of the index of refraction for constructive and destructive interference, so to shift by pi over 2, blah, blah, blah. At least I'm giving you this table here. So if you can understand how to use the table, you can understand which equation we use for constructive or destructive interference. This is a thin film problem. So here we have a thin film of thickness T, and it gives constructive interference for light with a wavelength inside the film of, I'm going to call that wavelength lambda sub film. And I'm going to also set that equal to lambda sub n, which means the wavelength of the light inside my material right here. Now this is a new type of problem. We're going to be asked to show that. We haven't really done these types of problems where we have to show something. So we're going to show that the minimum film thickness, which I'm going to call T sub min, of lambda sub n over 4 is needed in order to give us constructive interference. So that's what we need to get constructive interference. Okay, so let's recap. We've got a thin film of thickness T. We're going to have constructive interference. I'm going to say the wavelength of light inside my film, I'm going to call that lambda sub n. We're going to show
that the minimum thickness of this film, in order to get constructive interference, that means the reflected light to add together to give us a bright pattern instead of a dark pattern, the minimum thickness of this film has to be the wavelength of light inside the material divided by 4. Okay, so what's happening is that light is coming, incident light is coming from outside the film. It's striking the film surface. Some of that light's going to get reflected back toward our observer. This is my eyeball here. Some of that light is going to enter into the film, get reflected at the bottom of the film, and then come back and then get bent as it comes out. So those rays of light have to combine constructively in order for us to see constructive interference from our eyeballs. So this is a combination of light adding together constructively. That light is reflected off of the surface of the film, and is reflected off of the back surface of the film too. Okay, so we have to show that the minimum thickness, in order for us to get constructive interference, the minimum thickness of that film is the wavelength inside the material divided by 4. Okay, so how do we do that? Now the thing about show that problems, we're going to see some of these on our exams this year, is that I tell you what the answer should be. We should find that the minimum film thickness is the wavelength over 4. So these problems tell you what you're looking for, and you have to do all of the work to show me how to get this correct answer. So I've already told you what the answer should be. The whole idea is to show how we do all that work to get this answer. And that's really more like what we should be doing in physics, is working on the process to get that answer. Now, in order to solve this problem, we've got to figure out what equation do we want to use in order to get constructive interference from our thin film. Well, we've got this sort of truth table to help us figure out which equation do we want to use for constructive interference in our thin film, given the index of refractions of our material in those different layers. So we're going to assume for this problem that N2, the index of refraction of the film, is greater than N1. So we're going to assume that essentially outside the film we have air that has an index of refraction of 1. And on the other side of the film we also have air, index of refraction of 1. So this also tells us that N2 is greater than N3. So I'm going to say N1 is this first, the index of refraction outside as the incident ray of light's coming toward the film. N2 is the index of refraction inside the film. N3 is the index of refraction outside the film on the other side. So we've got air and air sandwiched around my film. Okay, so I know that N2 is greater than N1 because the index of refraction of air is 1. And N2 is greater than N3. Now let's utilize our thin film truth table in order to figure out which equation are we going to use in this case for constructive interference. So if we look at this, we see that the first column asks us, is N2 greater than N1? And in this case, N2 is greater than N1. So N2 greater than N1 is equal to true. The second column in our thin film truth table asks us, is N3 greater than N2? And in this case, it's not, because N3 is less than N2. So for that column in our thin film truth table, we're going to say false. So we're going to look on our thin film truth table and look for the row where we've got N2 greater than N1 is true, and N3 greater than N2 is false. So that's the third row, okay, on our thin film truth table. And so then it tells us for constructive interference, we're going to use 2t equals m minus 1/2 times lambda sub n. So lambda sub n, that's the wavelength of light inside our film. Okay, so we need to figure out what thickness do we need in order to get our first constructive interference. For m, we're going to use m equal 1 because we're looking for our first constructive interference. Okay, so then we've got 1 minus 1/2, that's just 1/2. So this is equal to 1/2 lambda n. So 2t is equal to 1/2 lambda n. And now we need to solve this problem for t. Okay, so I've got to divide both sides by 2. So t is equal to, okay, so we've got lambda n, and then I've got 1/2 divided by 2. Okay, so 1/2 divided by 2, that's the same thing as saying 1/2 times 1/2, because when I divide by a number, it's the same thing as multiplying it by its reciprocal. So you could always write 2 as 2 over 1. So this is the same thing as saying 1/2 divided by 2 is equal to 1/2 times 1/2, and that's 1/4. So t is equal to lambda n over 4. So here we just showed that the minimum thickness for our film for the first constructive interference is equal to the wavelength of the light inside the film divided by 4. So we, in one of these problems, these show that type of problems, we do the work in order to arrive at the answer they're looking for. So we always know what the answer should be, what we should be aiming for, and so then the whole part of the problem is to do the work to get us to that correct final answer. And of course, all the steps we do to get us to that correct final answer have to also make sense. Well, you're going to be given a workbook problem where instead of n2 being greater than n1 and n3 like we just did, you're going to have one where n1 is less than n2, and that's going to be less than n3. So the index of refraction is going to get higher as we go from n1 to n2 to n3. And in that case, you're going to be looking at your thin film truth table, and the first 2 columns. Is n2 greater than n1? And in this case, n2 is greater than n1, check mark. And in the second column, is n3 greater than n2? In that workbook problem, n3 will be greater than n2. So you're going to have true and true for the conditions for both of these columns here in your thin film truth table. And so then you can look down there to see what equations do you need to use in order to think about constructive or destructive interference for this particular workbook problem that you're going to have. You're going to have 3 layers, and n1 is going to be less than n2, which is going to be less than n3. And let's say that you're given the wavelength of light that's incident on the film. So if you hear that word, the wavelength of light that is incident on the film, that's just lambda. And then in order to get lambda n, which is the wavelength of light inside the film, lambda n is equal to the wavelength of light incident on the film divided by the index of refraction of that film material that's sandwiched on either side by n1 and n3. Okay, so keep that in mind as you're going to be working through some additional workbook problems.